AP Calculus BC, Unit 6, office hours for the corrective to review for the retest. So some problems to try. I'll try and point out some things I noticed when I was grading the test. So here I would look for common, easy to identify slopes like 0 or undefined. So here, that's going to be when y equals the absolute value of x, right? Which is the same thing as y equals x for positive x's and y equals negative x for negative x's. So if you plug, so this just depends on, right? Okay, so the zeros are going to lie on these lines. So y equals x for positive x's and y equals negative x for negative x's. So there's some. We could then just calculate some others and see what happens. I don't know if there might be sort of symmetry along this kind of V. If you plug 0 for x in and y 1, you get negative 1. And then if you plug 0 and then 2, you get negative 2. If you plug 1 and 2, you get negative 1. If you plug negative 1 in for x and positive 2, you get negative 1. So I don't know, I kind of see that V again. So maybe they'll kind of follow along those. If you plug in 1 for x, you get a slope of 1. If you do 2 for x and 1 for y, you get a slope of 1. If you do 0 for x and negative 1 for y, you get positive 1. So I wonder if this one will be positive 1. Negative 1 for x would be positive 1. And negative 2 for x and positive 1 for y be positive 1. So it seems to be that pattern, like I said. Negative 2 for x is going to be positive 2. So I wonder if these will all be positive 2. So 1, negative 1, positive 2, 2 for x, positive 2. Negative 1 for x, positive 1 for y, negative 1, negative 1 for x, negative 1 for y is going to be positive 2, and positive 2. Okay. This one right here would be positive 1, negative 2. 1 minus negative 2 is 3, slope of 3. So the slopes are also getting steeper. So I bet this one's going to be positive 3. 2 for x, yep, positive 3. I bet this one's going to be positive 3. Negative 1, negative 2, positive 3. But this one will be positive 3. And I wonder if these would be like 4 or something. 2, negative 2, yep, 4, slope of 4. Up 4, 1, so it's a little steeper. And this one should also give the same thing. So there's your slope field. Look for patterns. Okay, these next ones, multiple choice. So I'm going to kind of do the same thing. I'm going to look for the easy to identify slopes. So when is x minus y equals 0? It's going to be y equals x. So we're looking for a graph that has 0 slopes along y equals x only. So that seems to be B right here, right? And there's not another one to narrow it down from. This one equals 0 when x equals 0, which is the y-axis, and y equals 0, which is the x-axis. And so along both axes, you have 0 slopes. So look, 0 slopes, 0 slopes. This one has 0 slopes here, but not there. This one has 0 slopes here, but not there. So I think this one has to be D. When does this equal 0? When x equals 0, which is the y-axis only, and then it equals undefined when y equals 0, which is the x-axis. So it should look like it's going vertical along the x and flat along the y. Vertical along the x, flat along the y. So that's got to be A. So this is going to be when y equals 0, which is the x-axis. So 0 slopes along the x-axis. And it's going to be undefined when x equals 0, which is the y-axis. So vertical along the y-axis and flat along, vertical along the y, flat along the x. So that's going to be C. So I think that's, that's the quick way of doing it. Just narrow it down. All right. I don't know. You guys seem to do pretty well with that on the test. Eulers Method. Some of you totally have it. Some of you totally don't have it. And some of you guys are kind of in between. But, I would make the table, but you should remember how to create the table. You shouldn't memorize the tops of the table. Okay, all of this comes from the equation of a tangent line. We're using tangent lines to approximate values. So the tangent line would be y minus y1 equals m times x minus x1. I mean, that's just the equation of any line in point cloud form. So this is going to be the new y. This is the old y. This is the known y and the known x, which I'm going to call old. And then we have a new x and a new y that we're going to use this for. And then this is your derivative there. So the new y is going to equal the old y plus the derivative times, and what we call this difference between the new and old x is usually constant. We call it delta x. So if you make your table, we keep track of the x's and the y's, and then we need y prime, and we need delta x. And so we start with 0, 6, and the derivative comes from that. Delta x is going to be, it says step size 0.5. And so we're going to take step sizes of 0.5 to get from 0 to 2. Now, this is going to equal this plus this times this. So I'd like to add that also. So the new y equals the old y plus the derivative there. So the derivative here is going to be 6. So it's going to be this plus this times this. So that's going to be 9. And then this, we got to find the new dy dx. So it's going to be these two added together. So it's going to be 9.5. So it's going to be this plus this times this. So half of that's what? 4.75, 13.75. And then the new derivative is going to be 14.75. It's going to be this plus this times this. Now half of 14.75 would be 7.375. So if we add that to 13.75, 5, 12, carry the 1 to 10 is 11, 10, 20.125. So the numbers are starting to get a little intense. Actually, sorry, 21. Okay, the next one, next derivative is going to be 22.625. So we've got to figure out what half of that is. 11.3125. And then we're going to add 21.125 to it. So we get 5, 7, 3, 4, 2, 3. 32.4375. We don't need the last y prime. So that's how you do it, and you should be able to recreate it. So here's one that's already kind of set up for you. So we still need an extra column for delta x. You don't have to use the table approach. You can just recreate tangent line equations, but for ones that have a lot of steps like this pays off. If it's only 1 or 2 steps, then maybe just do it the other way, which is actually pretty typical in the AP test. It's just like a couple steps. Okay, this plus this times this. So we have a lot of it filled out for us. We have all the derivatives done for us, so this should go quicker. The step size is 0.5, right? 0.5, 0.5, 0.5. Don't need the last ones. Okay, so it's going to be this plus this times this. So that's going to be 4 plus this times this. That's going to be 5 plus this times this. It's going to be 8 plus this times this. It's going to be 7. So it can go pretty quick. with those derivatives already done, and the numbers be nicer. So the way we write this, though, for our final answer is we write f of 2 is approximately 32.4375. And f of 4 is approximately 7. So that's how we write the answer, label it, communicate that it's an estimation, right? Okay. Logistic growth. These are the ones that you can use the memorized couple things for. There's only two equations I want you to use. I want to use the definition, the differential equation for it, which has an exponential part, kp, and then it has this limiting part, m minus p. So I'd memorize that, and then I would memorize the solution to that differential equation, which we worked out. M over 1 plus a e to the negative mkt. That is all I want you to use for formulas, okay? So you could be given it to you already in this, and you need to make that a 1. So I'm going to divide a 2 out of everything on the top and the bottom. And some of you guys knew to do that on the test, but kind of messed it up, or like did it and then went back, like, and brought some parts of it back and some parts not. So the initial population p naught you just get by plugging 0 in. It's e to the 0 is 1, so it's 100 over 5, which is 20. So I mean that's easy. And then the carrying capacity is the thing on the top, right? So that's done. And the K value we get from here, because that's going to be negative MKT. So this number right here, negative MK equals negative 0.4. And we just found M was 100. And so then we can solve for K. And K equals, it's going to be positive. We're going to move the decimal point over 2 more spots. So it's going to be 0.004. Okay? Now, the time when the population is growing as fast as rate always happens at half the carrying capacity. So we're going to set the population equal to half its carrying capacity, which is 50. And then we're going to set it equal to the growth model, either the original one or this one. I think this one's easier. The numbers are smaller, but either way, but go with one or the other, not some weird combination of both. And then you just got to solve this, okay? So there was some formula I had in the notes and stuff sometimes, but it's not worth memorizing. This is simple enough math to do. You should understand this concept. That'll pay off actually more on the AP test. So 50 plus 200 e to the negative 0.4 t equals 100. We subtract 50. And we divide by 200. Now, I'm tempted to flip this so it doesn't have a negative exponent anymore. Either way, you could leave it in there or not. This is 1/4, so you'd flip that also. Actually, no, you shouldn't flip that yet. I haven't flipped anything. I just put the negative down as positive. Now I'm going to flip it to get it in the numerator. And then I'm going to take the natural log of both sides. And then I'm going to divide both sides by 0.04, which we could make nicer. That's 400. Did I lose track? Did I add another? Okay, it should be 0.4. So that's 4/10. So we could say 10/4. So we could say 5/2. Natural log of 4 is the time. Or 2.5. You could have left the negative here and took the natural log of both sides, and you get negative 0.4 t equals natural log of 1/4, and then divide both sides by this. And that's the same answer. That would give you -5/2 natural log over 1/4. Now what you could do is bring the negative inside as an exponent, and you would get our other answer, 5/2 natural log of 4. So either way. So those are your answers. P naught equals 20, M equals 100, K equals 0.004, T equals 5/2 natural log of 4. Okay, now this one is in the differential equation. So one, we should try and recognize this. Now we got to try and make it look like that. Last one we had to try and make it look like that too. So we know we want to factor a p out, right? And we do want the leftover minus p to be here, and we don't want any number in front of it. So we also want to factor out a 0.1. Okay, now when you factor out a 0.1, you're dividing it out. Okay, so you're dividing it out and putting it out in front as a factor. So here's the 0.1. Now if you divide this by 0.1, you get 100. So now that's in the form. Now this is your K, this is your M. P naught was just given to you. P naught was 5. So I guess just take advantage of that. The M value is 100. The K value is 0.1. If there was a negative in front, that would count also. So the only thing left we need is the last part. Now for the last part, we need to write the solution model so we can do what we did last time. So it's going to be P equals 100 over 1 plus AE negative MK. So that's going to be 10, negative 10T. We got to find the A value, and that uses the initial condition. So if we plug times 0 in, we get 1 plus A. We get 5 plus 5A equals 100. Subtract 5. 5A equals 95. Divide by 5. A equals 19. So now we can write this as 100 over 1 plus 19e to the negative 10t. So we have to figure that out first. Then we set it equal to half its carrying capacity. So we set the population equal to half the carrying capacity. So that's 100 over 2 is 50. And we set it equal to our model, and we solve for the time. It just takes a few algebra steps. So 50 plus 95, 950 e to the negative 10t equals 100. Subtract 50. Divide by 950, which gives you 1 over 19. Take the natural log of both sides. Divide both sides by negative 10. So we could say t equals negative 1/10 natural log of 1/19. We could bring the negative inside and say it's 1/10 natural log of 19. It's a little cleaner, whatever. So, either way, I'm okay with either answer. So, all right. So know your logistic growth equations, how to work with them. And then the other big part of the test was solving differential equations, which one might pop up as a logistic growth, but if you try and use the shortcut, I'm taking off half credit right away. And then if you mess up the shortcut, I'm probably taking almost all or most of the rest of the credit away. So I don't really want to use a shortcut. It's there, I guess, but you better feel really confident. And several people on the test tried it. None of them were successful. So I gave them like 1 out of 6 points, I think, best case scenario. I think it'd be better to just try it. You'd probably earn more points just doing it the regular way. But I would say that we had a lot of trouble on these problems on the test, a lot of just calculus integration errors, all different kinds of methods, using the wrong method, missing chain rule stuff. And then the other thing was getting the domain right, people just missing stuff for the domain. So we're going to separate the variables. We're going to move the y plus 1 underneath on the left-hand side, and then move the dx to the other side. So you got to do that right. So this is going to be natural log of y plus 1 equals natural log of x. If there was like an extra negative or number in here, you'd have to make sure you addressed it with the chain rule. Plus c. A couple people didn't even put the plus c on the problems. That's a lot of points I just have to take off right away. Use the initial condition to find the c value. So y equals 1. And when x equals negative 1, and that's going to be 0. So c equals natural log of 2. Don't need the absolute values anymore. I'm going to rewrite it. Natural log of the absolute value of y plus 1 equals natural log of x plus natural log of 2. I mean, we could combine these two or not. We're going to exponentiate both sides anyways. If you do that, rules of exponents say you could do it like this, right? And so that gives you 2 natural log of the absolute value of x. Now, to get rid of these absolute values, you have to do plus or minus, and that's a mistake that some people made. They didn't write it. If you don't write it, I'm just assuming you forgot and you got lucky. But you got to write it, and you got to plug negative 1 in and make sure it makes sense. If I plug negative 1 in, that's 0. And so this is all 0. And so what will y have? I don't know if that. If you plug 1 in, okay, hold on a second. Why do I have this natural log here? There's no more natural log. Okay, that's what's throwing me off. Okay, if I plug negative 1 in, I get positive 1, 2. If I plug 1 over here, I get 2. So it needs to be positive, and then we're going to subtract 1 from both sides. So it's going to be 2. Absolute value of x minus 1. Now, here's another issue. I took off points many times for several people. On these solutions of differential equations, you should never have absolute values in your final answer, because I guarantee that whatever the domain is, it's going to restrict it to one side or other of the corner on the absolute value. So it's either for sure you plug in positive numbers all the time and you can just drop the absolute values, or for sure you plug in negative numbers all the time and you could drop the absolute value and put an extra negative, which is what it does. So the domain, this doesn't have any domain issues, but the domain up here, x cannot equal 0, which on this graph would be obvious in the form of a corner. So x can't be 0, so I write the number line, I put it as open dot, single open interval. So whatever this is, even if it's like a boundary where you're like, oh, it could be 0, you're still going to make an open dot for these kind of problems. And then your initial condition, find where it lies, and then that's your chunk, your single open interval. So the domain is negative infinity to 0. The solution now we know we're plugging negative numbers into this absolute value, so we could just fix that and accomplish the same thing by dropping the absolute values and putting negative in front, which is what I need you to do to give you full credit. So that was a big issue on the test. Lots of people forget. Lots of people leaving absolute values in their answers. Okay, next one. We need to separate the variables. We need to integrate both sides. Write the plus c. If we plug in negative 4 here, this is going to be 16 over 2 is 8. And then natural log of 1, which is 0. So c equals 8. We're going to rewrite it. Y squared over 2 equals natural log of the absolute value of x plus 2 plus 8. Multiply both sides by 2. take the square root of both sides, 2 natural log absolute value of x plus 2 plus 16, plus or minus. Now, here's another thing. If you didn't write that in your work, I took off points right away. You have to write that. It can be positive, it can be negative. It depends on the initial condition, which in this case gives us negative. Because if you plug in -1, which gives you 0, plus 16 squared 16 is 4, but it needs to be -4. So we got to go with the negative. Now, last thing we need to do is figure out the domain. There's a domain issue here that x plus 2 cannot equal 0, so x cannot equal -2, which also comes from up here. So often the restrictions show both of these. We also know that y can't be 0, which is also an issue here, that this has to be all positive or greater than 0, which is, if you set y equals 0, it's this equals 0, you square both sides, you're getting the same thing. So we're really just trying to figure out, I'm not trying to keep track of the greater than or less than. I just got to figure out the boundary. When does that equal 0? So if you were to solve it, you would subtract 16, divide by 2, be -8. You would exponentiate both sides. You get rid of the absolute value by doing plus or minus, which I think there was a problem like that on the test and people didn't do the plus or minus again, and I'm taking off points all over the place for the plus or minus issue. And we subtract 2, so we have two answers. We have -2 plus e to the -8, and we have -2 minus e to the -8. Now we need to estimate what these values are, or we need to do a line check. So we know that x can't be that, and x can't be that, so we do a little number line. So -2. Now this is -2 plus a small number, so that's for sure to the right. And this is -2 minus a small number, so that's to the left. But they're both really close to 2, okay? So the initial condition, -1, is for sure over here. So this is your domain, but that's it. So the domain is -2 plus 1 over e to the 8th, comma, positive infinity. The solution has a negative square root. I don't want the absolute values in the inside of your final answer. Now we know we're plugging in numbers that are bigger than -2 already, right? So we know the inside of this is going to turn out positive no matter what. And so we could just put parentheses there. Once we figure out the domain, then we can get rid of the absolute values. Can't do it before knowing the domain. No absolute values in your final answers on these problems, okay? Because the domain will for sure restrict it in one case or another. Okay, this one, separating the variables, seems pretty easy. And then we're going to integrate both sides. Now, if you try normal kind of u substitution techniques here, they don't work. du equals 2x dx. That's a problem. It's not inverse trig. It's not inverse tangent. So we're probably going to have to use partial fractions. So we got to factor this x minus 2x plus 2. And partial fractions is an algebra technique that allows you to split this up. So we say, okay, well, that's going to be a over x minus 2 plus b over x plus 2. And we use the heavy side approach, where we multiply through by the least common denominator. We get 2 equals a x plus 2 plus b equals x minus 2. Some of you guys just didn't do this technique on the test. Now, all the techniques from this year that we've learned up to this point are fair game. So integration by parts are fair game. Now I'm going to plug in a positive 2, and that'll make that go away. And I'll have 4a equals 2, so a equals 1/2. And then I'll plug -2 in. That'll go away. I have -4, b equals 2, so b equals -1/2. I'm then going to rewrite this dy. So it's going to be 1/2. So it's going to be integral of 1/2 dx over x minus 2 minus 1/2 dx over x plus 2. Or whatever. We could put the dx out here. So we could write them as separate integrals or one integral. So the answer is going to be y. Just y equals 1/2 natural log of the absolute value of x minus 2 minus 1/2 natural log of the absolute value of x plus 2 plus c, of course. I'm going to combine these together because probably going to want to at some point anyways. Log rules. I'm going to use the initial condition. If I plug 3 in, I get 0 out. So if you plug 3 in here, you get a 1 on top, 5 on the bottom. So c equals negative 1/2 natural log of 1/5. You could also write that as positive 1/2 natural log of 5 if you want, or you could deal with that later. So there's your c value. So we're going to rewrite it. Y equals 1/2 natural log of the absolute value of x minus 2 over x plus 2 minus 1/2 natural log of 1/5. And I mean, this one's pretty close to done. I mean, I think we should kind of like combine it together better. So y equals 1/2 natural log of the absolute value of x minus 2 over 5x plus 2. Right, so that's a little better. Well, hold on. You divide by 1/5, so it ends up on the top. Now, domain 1, x cannot be negative 2, right? X cannot be positive 2 because that would make it natural log 0. The inside is supposed to be greater than 0, which means that it means it can't equal 0. So the top can't be 0, the bottom can't be 0. And I think that's enough. Like, I don't think we need to solve this one on its own. I mean, we could. You get x equals negative 2, positive 2. You could test a point. So usually you don't have to do all these test points and stuff on this. I don't think we need to do this because both those points are going to come up anyway. So I would just do this, put those points on there, and then find the initial condition, which is 3, and then you don't have to test points and stuff, like as if you're really trying to find. I'm not really interested in like the full-blown domain of this function. I want the domain of the solution coming from this differential equation, which is much more narrow. So the domain is 2 to positive infinity, and now we can rewrite our final answer without absolute values, because if we know x is bigger than 2, that's going to be positive, that's going to be positive. It's going to be 5x minus 10 over x plus 2. Right? Now, there are other versions of this you could write. You could bring the 1/2 inside. Now it's a square root. Whatever. Same thing. So that's it. Some good practice. Obviously, study your test. This is kind of more brief than your test was, but just some opportunities to practice some things and practice what you need to practice more to be absolutely ready. And just be careful with all the algebra on here and just the basic integration or the new integration and the plus or minus issues in the domain.